Good morning, everybody. This is the fifth series of lectures coming from the Chennai Mathematical Institute and National Academy of Sciences, Allahabad. And it's a pleasure to have Professor James Libby of IIT Madras give today's lecture. He has worked in many active research facilities in high energy physics all over the world. And he will be telling us some very interesting experiments. In India, we need many experimental physicists, especially in the area of high energy. And I'm sure this lecture will inspire many of you to look at this extraordinarily active area where fundamental things are being discussed. Now, I will request Professor Libby to start the lecture.
Okay, thank you very much, Professor Mani and Mr. Anand, who's been helping with the logistics for this invitation to give this talk. I'll just start sharing my screen a moment. Okay, I hope that's visible for everyone.
Yes, sir, you can go ahead.
Okay. So I'm going to be discussing several things today. The title really refers to what I'll talk about at the very end of this talk, which is the search for beauty. But I'm going to base this around the CMS experiment, which is one of the experiments at the Large Hadron Collider at CERN, Geneva. But there's quite a lot of history that I'll go through first before I get to this topic. So the outline of this talk is first to motivate experimental particle physics, what I refer to here as big science, and the way this has been built up through the 20th century, ultimately leading to the Large Hadron Collider at CERN, the LHC. Now, once we have our accelerator and our collider, we need experiments to use that facility, and then I'll talk a little bit about the Compact Muon Solenoid, the CMS experiment, and what it's most famous for, now getting on for nearly 10 years ago when it discovered the Higgs boson. And I'll describe quite a bit about the Higgs as part of this talk, as any talk about the LHC would normally do. And then I'll explain why CMS and LHC are still running and will run for a further more than another decade. And one of the things that it's doing is searching for beauty. And I will show a recent highlight from the experiment related to this and explain a different way of how we're trying to do experimental particle physics today. So particle physics is essentially in a long tradition of what I would refer to as reductionist physics, whereby in the scientific endeavor, people have always been trying to discretize matter into smaller and smaller parts. And this is very much an old idea. So even going back to ancient Greece and Democritus, the idea of the atom was there, but it was really formalized by Dalton in the 19th century. So just to understand how important this idea is that we can break down matter into smaller components, Richard Feynman, who I'll talk about again in this talk, said if we were to just keep one thing from everything we've learned about science up until now, he suggests that we put forward just the atomic hypothesis, that you can break up matter into smaller and smaller parts to try and understand its basic interactions. And that sort of gives you a sense of why this is such a fundamental idea underpinning not just physics, but other areas of science too. But the atom, with its size of around an angstrom, 10 to the minus 10 meters or so, is very much not the fundamental building block of matter. We can go deeper into smaller scales. So you'll be aware that the electron was discovered at the end of the 19th century, making clear that the atom itself was not one single block. And then further, Rutherford, who I'll talk about a little more, discovered the nucleus. And then it was clear that the nucleus itself was made of protons and neutrons. Then much later in the 20th century, not until the 1960s, the idea came about that the proton and neutron themselves were not truly fundamental, but they were made of objects which are incredibly small. So there are 10 to the minus 18 meters or less, and perhaps are just purely point-like objects, are the quarks and electrons. So what particle physics also does, as I'll explain in a bit, is look at smaller and smaller scales which correspond to higher and higher energies. And that's what we're looking at now at the Large Hadron Collider. So another question that's often asked about experimental particle physics is, why would we do this? We're not got a direct goal at any of this. We're looking for things that we really haven't even thought of in advance. And I like to think about this in terms of something completely unscientific. And I'm going to just show you this photograph. I'm not sure how many of you will know anything about this very famous photograph, but this is the expedition to Everest in 1924, where this gentleman at the back here, George Mallory, and one of his team got within probably a few hundred meters of the peak of Everest. And this was before oxygen and various other things. So it was, it took another 30 more years before Edmund Hillary and Tenzing reached the summit. But he's very famous because he was asked why he was going on these crazy expeditions and why he'd want to climb this mountain that looked completely inhospitable and ultimately cost him his life on this expedition. And he simply said, because it is there. And I think that's also a very good way of describing scientific endeavor without a goal of either saying inventing a renewable energy source or something, or finding a cure for a certain disease. We've always benefited from understanding the world more by looking more closely at it. And it's very important that these kind of areas of research are also followed, because they have untold spin-offs along the way. And I'll talk maybe a couple more things about that as I go through. So that's by some way of an introduction into the type of physics that we do. But I just want to now talk about the techniques that we've used as we've gone deeper and deeper inside the atom and found these fundamental building blocks. So a big breakthrough was when Ernest Rutherford discovered that the atom was in fact largely empty space, and it had this very small nucleus at the center which contained most of the mass. And how he did this experiment was to utilize the radiation that had been discovered by Becquerel and understood much better by the Curies, by taking a source of alpha particles, helium nuclei, and bombarding them onto a very thin piece of gold foil. And what he observed in terms of the pattern of how the alpha particles were deflected as they went through this foil told him that essentially there was this positively charged minute center to the atom, which he identified as the nucleus. But this idea is what we still do today, where we're scattering particles off one another. Here he's scattering an alpha particle off the gold nucleus. And essentially that's what we still do in most particle physics experiments. We're just looking to get two particles to interact with one another and then watch what happens once the interaction has happened. And how Rutherford did this was to have his postdocs, I think at that time, Geiger and Marsden, to basically count one by one the flashes of light caused as the deflected alpha particles hit this fluorescent screen around the apparatus, and they had been ticking them off one by one. And this was the very first sort of particle physics experiment. And the detectors we now use are far more sophisticated. And one of the first types was the Geiger tube, which was an electronic device to detect radiation invented by Geiger, because this was a very painstaking process to count individual interactions. And we'll see that the technology has evolved a great deal now over time, so that we can do very sophisticated measurements of such scattering processes. Now, the other thing, as we've moved deeper and deeper inside the nucleus, is we've benefited from the fact that during the revolution of quantum mechanics, this concept of wave-particle duality came about, whereby it was realized that any particle that's moving has a corresponding wavelength associated with it. This is the famous de Broglie wavelength formula, where the wavelength lambda is Planck's constant divided through by the momentum of the particle. So the important thing to take away from this formula is once you have a particle of very high momentum, you get to a very short wavelength, much shorter than what you would have for, say, the nanometers of optical light. So you are able to see with these particles, not in the way that you think of looking at by using your eye, but you can see using other things, scales that are much, much smaller using very high energy particles. And now at the LHC, we've got the very highest energy, so we see the very smallest scales. So I could go on for a long period of time describing the whole evolution of the standard model of particle physics, which has come to describe pretty much all the matter that we've managed to produce here on Earth, and also 3 of the 4 forces that act between these pieces of matter. And it's pretty much withstood every experimental test that we've thrown at it. Some parts are incredibly well measured. Here, the coupling strength of an electron to a photon, for example, in the standard model, is measured to this tiny percentage. So I'm counting my decimal places here. I think it's 1 part in around 10 billion, 2 parts in 10 billion. So this is incredibly precise measurements are made. And there's a lot hidden in this, but this is a formula that describes all of this. It describes the forces, it describes the particles themselves and how they interact with one another. This is the so-called Lagrangian of the standard model. And this is so compact that you can fit it on a t-shirt. So when I'm giving this live in the past, this lecture, I will have my son or daughter come up wearing this t-shirt so you can actually see that this equation is a rather simple form. Now, you're not to be too worried about anything in or written on this in this expression, but this 0 with a line through it, the Greek letter phi, is the one thing I want you to take note of. So in this lower half of the equation, this phi appears. And this phi is the so-called Higgs field, which leads to the Higgs boson, which was the thing that drove the quest to build the Large Hadron Collider. And you see it's in more than half of this one equation that describes all of this particle physics. So it's highly fundamental and important to the operation of this model working, or the way this model works. So the Higgs has got a very strange reputation, and people have made links to religion through it and called it things like the God particle. But there's actually an amusing story about why it's called the God particle, and this comes from this gentleman, Leon Lederman, who was a Nobel laureate himself for some of the discoveries that he made that helped substantiate the standard model. So he wrote a book about the search for the Higgs boson called the God particle. And he then tells a story about how this got the title of this book got its title. And he says this boson is so central to the state of physics today, so crucial to our final understanding of the structure of matter, yet so elusive that I've given it a nickname, the God particle. Why God particle? 2 reasons. 1, the publisher wouldn't let us call it the goddamn particle, though this might be more appropriate title, given its villainous nature and the expense it is causing. And then, of course, he then makes the connection with the more deeper meaning of perhaps this is part of the final answer of understanding the origins of the universe. But this is telling us that this particle was hypothesized at the same time that the quarks were discovered in the 1960s by Peter Higgs and others. And then particle physicists had been searching for it for almost 50 years, and it had yet to show up anywhere. Hence, the experimentalists like Leon Lederman became very, very frustrated and gave this name to the particle. But before I tell you about how we finally found it, I should tell you a little bit about why it's so important. And why it's important is it's the way that we understand the generation of mass in the Standard Model. Without the Higgs boson, everything would have to be massless, and that doesn't describe the world that we see. Now, mass we know is there because gravitational attraction between two massive particles is a very familiar feeling for everyone and describes everything we see around us on the Earth's surface, and then when we look up in the night sky. So we know gravity is there and we know mass is a property. But it was hard to describe in the Standard Model until the idea of the Higgs field, which in this cartoon is being represented by this crowd of people in a room. They're having a party of some kind, and they're actually all people related to politicians, as you'll see from the analogy that I'll build up in a moment or two. And they're sort of evenly spaced throughout the room, and they're enjoying their party. But if a famous political figure came into the room, they would all start gathering round them. So I imagine many of you are far too young to know who this lady is. This is Margaret Thatcher, who was Prime Minister of the United Kingdom at the time that Professor David Miller came up with this analogy to help get the LHC funded. So I've updated it slightly, so you're more aware of what I'm talking about. So here Modi ji has entered the room and people are desperate to see him. So they all gather round. And this means that as he tries to move across the room, his movement will be impeded by the number of people that are around him. And this is what the Higgs field does. If, say, a particle enters the field, depending on which particle it is, or it will get more of this field around it and slow it down and give it this property of mass. Now, depending on how important you are, you'll get more of the field around you and you hence become more massive. So you can think these politicians are more like the heaviest particles we know. But there's also other ways that this field can give a localized region of mass. And this is described by someone coming into the room, perhaps to say some rumor about what's happening next in an election or some policy is being announced. And once he's announced this, the field will again gather round and spread this around the room in clumps. And this is a sort of excitation of this room of people. And this is the Higgs boson. If the Higgs field exists, you'll be able to create this excitation and see it when you do particle physics experiments. And this group of people here is the Higgs boson. And this is what we were looking for. So the Large Hadron Collider was principally built to discover the Higgs boson, which it has done, and I'll describe that in a moment. But there are also other problems with this Standard Model. Even though it explains all the matter we see in the lab, it does not explain what we see when we look up in the night sky. This is an interesting talk all alone about what dark matter is. When we look at the night sky and make observations of things like the rotational speed of galaxies and how the cosmic microwave background behaves, we know that the fraction of matter that we see that's related to atoms is very small in the total matter budget of the universe. And dark matter is at least 5 times more than the regular matter coming from these cosmological observations. There's also dark energy, which is a much more difficult problem to assess as well. And again, a talk for another day. But it's not just the fact that we don't have in the Standard Model any particle that can describe this dark matter. There are many other problems as well. One thing is that we live in a matter-dominated universe. But the Standard Model of particle physics is pretty much symmetric between matter and antimatter. And we produce equal amounts of matter and antimatter in our particle collisions, apart from very small differences that are seen in certain types of quark decay. I'll talk more about quarks and those type of quarks towards the end. Also, this theory takes a large number of parameters measured by experiment. And to get the theory to work, you have to fine-tune the numbers of this theory. So you have to actually take a number to its 18th decimal place to fine-tune what that digit is to get the theory to work, which seems a very unnatural thing to do. This is to make the Higgs mass what we see it to be. And then the structure of threes of everything and why we have more than one generation, as well as the final link to gravity, is not included in the standard model. So this is what the standard model looks like, less the Higgs boson. We have what are called quarks. The up and the down make up the proton and the neutron, but we have heavier versions of these as well, called the charm, the strange, the top and the bottom. And then similarly, we have an electron and then heavier versions again of the muon and the tau. The muon 200 times heavier than the electron. Famously, when this was observed for the first time, Rabi said, "Who ordered that?" It doesn't seem to make any sense that we'd want to have these heavier versions of the particles. And then on this side, we have what are called bosons, which carry the force is between these elementary particles. So there's the photon, which is responsible for the electromagnetic interaction. And then there's the gluon, which holds together the nucleus, so only interacts with the quarks. And then these Z and W bosons, which do the weak interaction, which leads to nuclear transitions or nuclear decay, such as beta decay. So this was our view of the standard model. I've forgotten even about neutrinos. They're the partners, the neutral partners of the electrons, and they're very, very light, though they do have mass. It's another mystery in the standard model. So this is our picture. And what's interesting about this picture is that these have ever heavier masses. So the up quark, for example, is around just 1 mega electron volt in mass. Sorry, I can't do the conversions to kilograms now. But the top quark is 175 giga electron volts. So it's 5 orders of magnitude different in terms of its mass. So this more massive particles required better technology to discover them. And that technology is the particle accelerators. So basically, Einstein gives us the answer to why we want to do this. So his most famous equation is E equals mc squared, which is equating energy to mass. And if we're interested in making things that are massive, such as some of these particles in the standard model and also the Higgs boson, we need to put as much energy as possible into a small localized area to generate these particles. So the first thing that we need is lots of energy in a small space. And that's done by the Large Hadron Collider. And they're reaching temperatures and energies that have not been seen since a trillionth of a second after the Big Bang. So that at one stage, the universe was highly compressed and all the energy was in a very small volume of space. And this corresponds to very high temperature or energy density as well. And that's what the LHC does. And then it can find these exotic particles that are duplicates of the lightest ones that we see in the standard model. So taking this idea, the Large Hadron Collider was conceived. And what it does is just collide 2 protons together with very high energy. 7 tera electron volts each is the design. So that's 3 orders of magnitude larger than a giga electron volt is a tera electron volt. And once they collide together, this puts a lot of energy in that small space, that 10 to the minus 15 meter cubed kind of region that's there for the proton. So its title, large, is just because you'll see it's very big to maximize the energy that it can produce in these collisions. This word hadron is the word we use to describe all matter that's made up of quarks, and protons are a type of hadrons. And in special running, the Large Hadron Collider actually collides nuclei together, or a proton with a nuclei, to study the strong interaction. And collider, there's a big increase in energy if you have both of the particles moving. So even the complications that you have to bring these minute objects into collision with one another by having them circulating in opposite direction is more than compensated by the very large gain that you have in the energy available to make new particles. So that's why we collide them together. Now, all of this is done in a collider just using electromagnetic fields, and they're used to manipulate the protons in different ways. First of all, one has to bring them to very high energies by accelerating them, and then they must be contained so that you can bring them into collision, and that collision also requires manipulating the particles in space. And this is all done within a closed loop. So these are circular or quasi-circular objects, as you're probably aware. I'll show you a picture in a moment. But this relies on electromagnetism that you know about. So we can accelerate using the Lorentz force between different regions at different potentials. So as a particle enters, it can be accelerated if you have an electric field in this direction. We actually use oscillating AC electric fields to do this, which is beneficial to how the accelerator runs. So we use RF or radio frequency cavities to do the acceleration. This is an example of one here, which produce large electric fields per meter. So here's 5 megavolts per meter type cavity. And as they're in a circular loop here, they can be accelerated many, many times to get up to the energy that we need. But to be contained in this circle, we use the fact that a charged particle moving in a direction that's perpendicular to a magnetic field will be constrained to move in a circular orbit. So if you increase the magnetic field as the particles accelerate, you can keep them in the same orbit. This is so-called synchrotron. So we're just using the Lorentz force law, essentially, to hold our particles together in the collider. To do the collision, we use different magnetic fields to quadrupoles, octopoles, to bring the particles into collisions. So the LHC itself is in Geneva, which nestles between two ranges of mountains on the Swiss-French border, the Alps and the Jura. And the site itself spans the border. The accelerator, though, sits 100 meters underground. And in one long tunnel, protons are accelerated in opposite directions and then brought into collision at various points around the ring. So I will talk more about the CMS experiment here, and it has a twin called Atlas, which is very similar at the opposite side. Then there are smaller experiments dedicated to different types of physics. And it's very large. It has a 9-kilometer diameter, and it's roughly 100 meters underground. The reason it's underground is not because it's dangerous, but because it was very expensive to try and buy all the land on the surface to build this. And then you have to dig down to be in a stable layer of rock. So this is why it was built underground. So the history of this project is lengthy. So it was conceived back in the 1980s while they were building a precursor to this, which was the Large Electron-Positron Collider that went in the same tunnel and collided together as electrons and positrons and studied the Z boson and the W boson very precisely. And there was a rival experiment that was to be built in Texas in the US, the superconducting supercollider, but this was cancelled in 1993. Once its site had been chosen in Texas, other places weren't so interested to support it, and there was political will went away to build it. So with this cancelled, the world's community of high-energy particle physicists decided they wanted to build the Large Hadron Collider at CERN, and it was approved in 1994. and the detector construction started during this period. Then for about a decade, between 1998 and 2008, the construction took place, and it was slow for a variety of reasons. One is money. I'll talk about the money a little bit more in a moment. The other was the superconducting wire required to build some of the magnets, and I'll also talk about that. Then finally it started running in 2010, and within 2 years it had discovered the Higgs boson. I'll talk about this. And now it's been running from 2014 to 2018 at a higher energy, and then it stopped in 2018, and it's being upgraded at the moment. And then it will start again, maybe now in 2022 because of COVID. And it will run with further upgrades until the middle of the next decade, the 2030s. And I'll explain what it's doing towards the end of this talk in that period. And because of the discoveries of the Higgs boson, Peter Higgs and François Englert won the Nobel Prize for their prediction of the Higgs boson in 2013. So to talk about the cost, it's estimated that over this long period of time, including manpower of the people who built it, it cost around $13 billion, which in these times of bailouts for COVID and one thing or another actually does seem like quite a small sum of money now. But it's a lot for a science experiment. But people have broken this down, that over the 2 decades where the United Kingdom was funding the construction of this project, for example, which is one of the biggest contributors to CERN, 4 countries provide most of the money to CERN. Those are France, Switzerland, Germany, and the UK. UK is one of the largest contributors. They worked out that for every single taxpayer in the country, it was equivalent to buying 1 cup of coffee a year for this project. So it was only a few pounds, not very many pounds, that were being spent per person to fund this project. So put in this way, the public don't mind, given the vast sums of money governments tend to waste on other things. They see this as a worthwhile thing to be doing. So big science is expensive, but once you break it down, it's really not so much. So I said that the delays were caused by this superconducting wire, which lies at the heart of these big blue tubes, which are the dipole magnets that hold the protons in their orbits as they go through this 27-kilometer long tunnel. And the magnetic field in these magnets is 8.3 Tesla, which is 100,000 times larger than the Earth's magnetic field. So to produce such a large magnetic field, one has to use technologies where you can produce very high currents. And as you'll know from your Ohm's law, that if you have high currents, you will get a lot of heating if you have any resistance in the wires. So that meant that the wires used to produce these large magnetic fields had to be superconducting. And these superconducting wires require a huge number to make all of these dipole magnets around the ring. And each one is some 30 meters long. And there are some thousands of these around the ring. So this took a long time to produce the superconducting wire, wind the coils, and produce these magnetic fields. So actually, most of this blue tube is just the cooling, the refrigeration that's required to make sure that these wires are kept superconducting. So they're actually at the temperatures of about 2.2 Kelvin, I think, which is colder than outer space, which is used to cool the magnets so that they can run in a superconducting way. So there's no loss and no heating due to resistance in these wires. So once you've got your accelerator working, what do you see? So this is a picture of a real event inside the CMS experiment that I'll talk about in a moment. And protons collide at the center here and produce a spray of other particles using all that energy that they have to make mass and make particles. And the charged particles we managed to see as these lines. They're leaving tracks in the detector. And then these blocks are bursts of energy that we collect. And we can collect this energy and infer where the particles interacted with our detector. So this is what you see. And I'll come back to these two very distinct red objects here in a moment or two. So this image is built up by the CMS detector. Now this is the one of these two very large detectors at the Large Hadron Collider, which study these proton-proton interactions and discovered the Higgs. So when I say large, these things are multi-story buildings. So they're 15 meters in diameter. So with all the ancillaries, it's around 20 meters tall. And it's also around 20 meters long. And this is actually much smaller than Atlas. Atlas is much bigger, but this is still a very large object and has a weight as over 12.5 kilotons. And what it does is record the traces that all those particles produce as they go away from the collision point from the LHC. So the LHC collides the particles at the very center of this detector. And then there are dedicated devices all the way around, which are used to identify the different types of particles and measure their properties after they've been produced. And so this word solenoid is yet another magnet. There's a solenoidal field here, which means that all the charged particles will bend. And if you measure the curvature, you can measure the momentum of the particle. So that's why it's a solenoid detector. And particles, once you've measured their momentum, will interact with all this mass that sits around here. And there are two dedicated types of what are called calorimeters, things that absorb the energy that are produced by the particles. One is for electrons and photons that are produced. It's called the eCal. Don't have to worry about why it's called that. And then there's one to collect all the other hadronic particles that are produced in this, these interactions. Now, there's one type of special particle called the muon, which is the heavier version of the electron, which doesn't really interact at all with all of this material, or interacts very little with this material. And it escapes the detector. And so there's another set of detectors outside which measure if you've created a muon, this heavier version of the electron or not. And so these are the sort of main pieces of the detector, the CMS detector. I don't have any time to talk about the different technologies that are used, but if you have questions, you can ask me in the Q&A session. So coming back to our picture, what you're actually seeing here is a Higgs boson event or a Higgs boson candidate, where the particles came into collision. There's this big spray of stuff from the two protons, remnants of the two protons. But then there are two clusters of energy. This is in this eCal detector for photons and electrons. And because there's no charged particle pointing at these dashed lines, it means that there were photons. So these are two photons with a lot of energy back to one another. And if you look over many, many collisions and you work out what caused this, what's called the invariant mass, or the energy, the rest energy that led to these two photons, what you see, I don't have that photo, I have another one, you'll see a peak build up. This is actually in the 4 lepton channel, 4 muons and 4 electrons. Sorry, I should have had the 2 photon channel here. But it's the same idea. You have your Higgs going to 4 leptons, you have your Higgs going to 2 photons, and you all pile up at one distinct value of the mass, which is 125 GeV. And this was done in various experiments, in both CMS and Atlas, and in various decays, Higgs to 2 photons, Higgs to 4 leptons. And in July 2012, they announced the discovery, many happy particle physicists, and this standard model is complete, this H Higgs boson. It's the only particle that has no spin that's been observed in the standard model, and it matches perfectly to what Peter Higgs and others thought could give mass to all the particles in the standard model using the Higgs mechanism I described earlier. So in the last 10 minutes or so of this talk, I want to explain why this wasn't the end of the story, why we didn't stop in 2012 once we've discovered the Higgs, and why it's going to continue running actually for a further 20 years. There's still many things not understood. Where is this dark matter? What is it? Can we produce it in the laboratory? We don't really understand at all this matter-antimatter asymmetry. The Higgs mass coming in exactly where the standard model says it should be, with these fine-tuned parameters, but no other particles, is not helpful at all. Where are these other particles that could be helping to remove this fine-tuning? And we're looking for those actively. And these extra particles are really essential to answer these questions about dark matter, also this asymmetry, and also why we might have these 3 generations. And even some theories bring you a link to gravity, but gravity being so weak is very hard to test in the laboratory. But one tool we have to do this is to look at beauty or bottom quarks and their decays to try and understand if we can get some hints as to what's going on to address some of these other questions in particle physics and deficiencies of the standard model. So this beauty name comes about because of a quote from Keats. So this is a nice place where arts meet science. So they were talking about what to call these quarks. And initially they said, beauty is truth, truth is beauty, which is the last line from a famous poem by Keats when he's talking about this beautiful Grecian urn. He says, ye know on earth and all ye need to know. So saying that truth and beauty is all one needs, which is a very romantic ideal. It was an ideal of the Romantic movement. So these 2 quarks, because they were filling out the sort of symmetry of the standard model, were given the names beauty and truth. Today, they often get called bottom and top, which is a bit more prosaic. But the beauty is still used to describe the B quark at times, but truth has fallen out of fashion. So how this works is back to Richard Feynman, who I mentioned earlier. So he developed the first prototype to the standard model of particle physics, what's known as quantum electrodynamics, which is part of the standard model, which explained the interaction of electrons and photons. The theory developed more so we could describe the interaction of all the particles and all the forces. But his great intuitive aid to this was to say we could do this using diagrams, these so-called Fyman diagrams, where over a very short period of time, we can look at each particle interaction using one of these diagrams. So each line corresponds to a particle. And here we have several quarks, bottom, top, and on the right-hand side, we have leptons, muons, and neutrinos. And in between, we have the force carriers, which are weak ones, the W bosons. And what's interesting about this is that these particles here are much heavier than the ones on either side. The beauty quark is only around a 40th of the mass of the top quark, and the W is around 20 times larger in mass. So these particles that live for a very short period of time don't actually have to have their real masses. They're called what are called virtual particles, and they mediate all interactions in the standard model. And this is an example of a rare decay involving this beauty quark, where it annihilates with an anti-strange quark to give these leptons in the final state. And this is very rare. So every time you produce one of these combinations of quarks, the B and the S bar, beauty and the anti-strange, only 3 in 1 billion will actually decay in this way. So to give you a sense of that, I'll refer to the Indian cricket team. This is the squad that went to the World Cup last year. And here we have, I think, 15 people was the team, led by Virat Kohli. And in a country of 1.4 billion people, you have to pick out your 3 favorite players from this to have your 3 in a billion. So my personal picks of the 3 best players would be Kohli, Sharma, and Jasprit Bumrah, but you could probably argue with me about this, and I don't want to get into that. But just to show how rare this is, these particles are these very rare, most talented cricketers of their generation in India. So that's the equivalent of what we're looking for here. Of course, some players are rarer still, and because I'm an Englishman, I've got to put Ben Stokes in here, and he's an even rarer type of person. So back to my diagram and why this is interesting. Essentially, these virtual particles could be some of these new particles beyond the standard model that don't sit within what we know. So by studying these kind of decays very, very precisely, we can see if there's some new heavy particles in this loop that are contributing to increasing or even decreasing the rate of this decay. So this is why such rare decays are of interest in particle physics today, and why we're generating more and more data so we can look for these very rare type of processes, amongst many other things that are going on at the Large Hadron Collider. And CMS can measure this type of decay because of these muons having this property that they penetrate through all of these calorimeters that are trying to absorb the particles that are produced and then are detected on the outside. If such a BS to mu decay takes place, muon anti-muon decay takes place, you will see a pair of muons, which again, if you work out their total invariant energy or their rest mass, will peak at the invariant mass of this pair of beauty and anti-strange particles, this so-called BS meson. And this was a news article about this last year. It was one of the highlights from the last the most recent results from CMS. And they actually see this decay. They see this 3 times in a billion decay. This red region here is the number of events. And currently the measurement is not precise enough to know if there are any additional contributions. It agrees with the standard model. But with 50 times more data, which will be taken in the next decade or so, we'll be able to measure this much more precisely and see if there's any room for a contribution from these beyond the standard model particles. And if there is, it will help us tell us what they might be. And we can learn more about these outstanding mysteries of the standard model. Okay, so that brings me to the conclusion of this talk. So I've told you about the motivations for experimental particle physics, the Large Hadron Collider, and how it's been successfully running since 2009. Its most famous discovery, the Higgs boson, and how it completed the standard model of particle physics. But there's still a lot to understand. I cannot emphasize this enough, that we only understand 5% of the universe that we see. We understand the hydrogen in stars, essentially, and then some of the heavy elements that make up a tiny fraction of the mass. But everything else is a mystery. So the Large Hadron Collider and CMS are going to continue taking data for many more years to come. And they will make more and more precise measurements, and precise measurements such as those of the BS meson will allow us to understand, or at least hopefully see, what's next for particle physics. And we can see how the next discoveries can be made. And this is very much a story where you can get involved, given the timescales involved. All right, thank you. I'm finished now, and I'm ready for any questions.
Thank you, sir. Participants, we will take. We'll just pause for a couple of minutes. I have pasted a feedback form in the chat box, both in the YouTube live stream and as well as in the Zoom chat box. We'll just pause for a couple of minutes. We'd appreciate if you can just fill that in, and then I will paste yet another form for you to ask your questions to Professor Libby. Thank you. We just pause for just about 120 seconds.
Okay, I'll just get some water, and then I'll come back.
Sure. Yes, Manisa, we can hear you. Could you switch on your video as well? Manisa? I don't know. I think Manisa just went out of the meeting. Okay, I think we'll get. Yeah. Okay, now I'm posting the feedback form. I'm sorry, the question answer form. You can start asking questions to Professor Libby. Professor Libby, I'll share my screen with you, so you will see what's the questions. So can you see the question?
Yes.
Okay.
So the question, everyone can see this, right? Or should
yes,
I read?
I think it's better that you read it out once and then everybody will see it.
Yeah, so the question is, what is the probability of antimatter getting formed in a hadron collider? And for how many seconds can we hold it so that we can harness energy from it? So, unfortunately, it's a myth that antimatter will form a source of energy by us creating it, because we have to put in far more energy to create it in the first place than you would get out. We have to, it's basically, you balance it at the very least. At the very best, sorry, you balance what you put in and what you get out. But the probability of producing antimatter is essentially in the standard model. When we make particles in these collisions, half of them are matter and half of them are antimatter. So in each collision, the probability is essentially 100% that some of the matter is going to be roughly 50% antimatter. I say roughly because in the standard model, there is a way of generating a little more of one over the other by, it's not enough to describe what we see, the imbalance we see in the universe. But when antimatter finally interacts with matter as it goes through the detector, it will ultimately annihilate with the matter in the detector. So, and just lead to a burst of photons or some other energy. So we can't harness it. So so I didn't talk about how frequent the collisions are, but they happen every 25 nanoseconds. And then the next collisions come. So the antimatter lives for a very short period of time before it gets absorbed somewhere in the detector. If it's an anti-muon, it will fly out. And but it's not, we can't think of harnessing it in that way because the particles are very short-lived and and they just decay. There are dedicated experiments at CERN actually, which make more stable versions of antimatter. They actually make anti-hydrogen. Project called Athena, I think it is, where they get an antiproton and a positron together and make the antimatter version of hydrogen. And then you can actually do things like spectroscopy with that hydrogen atom, anti-hydrogen atom, and compare it to hydrogen, and you can make very precise tests of the standard model. But it's not done as a way to get energy, because you have to put in energy to make the mass of the antiparticle in the first place, and all you'll ever get back is the mass of the particle. So it's not an efficient form of energy or of explosives, independent of what you've seen in science fiction films and Dan Brown movies and things like this. I'm sorry, but it's not going to be solving any problems in terms of energy anytime soon. And we know in the universe that there's not large amounts of antimatter out there, because if there were, there would be a region of the sky where the matter and antimatter came into contact with one another. And this would be a huge fireball that would light up the sky as the matter and antimatter annihilated. And we see nothing like that. You know, we do not see antimatter. Okay. Where are we? Which question should I look at, Anand? Can we break quarks? Maybe. We don't know. So we haven't got any evidence to suggest that quarks are not elementary particles. They are indivisible, like we think the electron is. However, it's possible at very, very high energies, they do become divisible. We just haven't reached those kind of energies yet. And we don't, it's not a particularly attractive theory to describe what the deficiencies of the standard model, such composite particles, as they're called. But it's also attractive historically because we're on this pattern or journey where we've continually been able to split the atom, then the nucleus, and then the nucleons, and why not the quarks? But there is no evidence yet, and I forget the numbers, but the scales are very, very small, so 10 to the minus 20 odd meters we're talking about for the size of the compositeness that might be there. But that's all we can do, is set a limit on it, because we can't go any further experimentally. Yeah, so each individual collision of two protons has roughly the same amount of kinetic energy as a mosquito or a few mosquitoes flying around. So the energies involved in the individual collisions are tiny, okay? But we actually have a lot of energy stored in the machine and in a very small space, and that's what allows us to do these kind of measurements. It's the fact that it's the energy density that matters for us, not the individual energies themselves. So it's not something, again, that would start some sustainable reaction like you're imagining from what you understand of fission reactions, for example, where you have the much heavier nuclei which are allowing you to access that bit of energy and those few neutrons that then perpetuate the fission process. So we record their flight path, really. So it's their positions as they go through the detector. And the nature of that path tells us two important things. One is the charge of the particle, because it curves one way or the other, depending on whether it's positively or negatively charged in the magnetic field. You're aware that the force would change sign, depending on the sign of the charge. And the other thing is the radius of curvature of that track can be directly related to the momentum of the particle, as long as you know the strength of the magnetic field, which we do to a very high degree of accuracy. So we do both. We measure the positions, and then we convert that into a momentum. I refer you to the answer I gave before, because it is there. Okay? We have, throughout history, we've understood things better by looking at them and studying them. So I will tell a short anecdote now about Faraday. So Faraday was doing a demonstration of the way that he could induce an electric current by moving a conductor through a magnetic field. And he was using it to show a light bulb, very rudimentary study in the 19th century. And this was at the Royal Society in London. And in the front row of the audience was the then Chancellor of the Exchequer of the United Kingdom, a very famous politician called Gladstone, William Gladstone. And he is supposed to have asked Faraday, what's the point of this? Why are you going to all this effort to show this? What's the use of it? To which Faraday replied, one day you'll tax it, which is very prescient because, you know, the energy industry revolutionized how the 20th century was. So it's, as I said, with particle physics, a priori, we can't say what questions things are going to answer when we look at things. It may throw up huge surprises when we understand what dark matter is, and we will gain great insight into the universe and how it works. And from that, we might be able to harness something. Who knows? It wouldn't make it fun if we knew the answer already. We're looking for those answers. And in the way we do this technologically advanced detectors and accelerators, they're actually spin-offs which have more immediate technological impact. So famously, the World Wide Web was invented as a collaborative tool at CERN to help the previous generation of experiments. And Tim Berners-Lee then came up with all these ideas for how you could have this linking together of pieces of information to aid the collaborators. And that's, you cannot imagine a world without the World Wide Web. And the fact that he made it non-proprietary and no money was ever made by CERN from this was also extremely important. More immediately related to the LHC, the magnet technologies that are used in those dipoles are also being used in the next big fusion project that's being built in the south of France, the ITER project, of which India is a part, which is trying to make sustainable fusion clean energy for the foreseeable future from seawater. So there are technological impacts on the short term, long term, who knows? So the graviton question. No, so the one word answer to this is no. I think it's very hard for us to include gravity in what we do in particle physics. And the reason for that is gravity is very weak in comparison to these other forces. So it has negligible impact on all the measurements that we make. So it's hard for us to infer anything directly about the quantum nature of gravity, of which the graviton is hypothesized to be the force carrier, right? However, there are things that might be discovered at the Large Hadron Collider which will give us pointers to what is this theory. So for example, okay, sorry, I forgot to read out the question. So this is, will the graviton be made part of the Standard Model soon? And what is the probability of finding the graviton? Sorry, Anand. So the theories of quantum gravity, many of them are based around what's called string theory. And string theory works at energy scales and length scales that we cannot probe experimentally at all. But we may have some indications if we discover many exotic things, particularly related to a theory called supersymmetry, which is why you may have heard of something called superstring theory. So string theories are what are called supersymmetric. And if we see some evidence for this supersymmetry, which is something theoretically strongly believed, but unfortunately there's no experimental evidence for it yet, this would give an indication that might be a pointer towards this kind of theory being close to a correct quantum description of gravity. However, I think people now feel we'll probably learn more about gravity from gravitational wave measurements and other cosmological experiments than we will directly from particle physics, because there gravity is dominant, and hence you see gravity without all the electromagnetic strong interaction and weak effects that are obscuring whatever gravity is doing in our particle interactions. Okay. So if particles, oh no. So so explain about particle physics beyond the standard model in a nutshell. So the standard model has this set of things in it. It has all these quarks, it has these leptons, the charged leptons and the neutrinos, and it has these 4 force carriers. And with that, we can describe everything that we see up to the limit of those anomalous things that are out there, this matter-antimatter asymmetry, the dark matter, why we have to fine-tune these parameters, gravity. So beyond the standard model of physics will be physics that explains these other things, while also including the whole of the standard model. It can't negate the standard model, it can't throw it away. It has to be an extension of it in some way. So you add new particles, usually at higher masses, otherwise we would have seen them by now. So these theories that add these additional particles to the standard model are generally called new physics beyond the standard model in some way. And they're of different varieties. There are supersymmetric ones, there are technicolor ones, there are things called little Higgs, there's gravitational excitations, Kaluza-Klein, ADS, all sorts of things you can have. That's not my job as an experimentalist. I just look at the data, and once we see something, the theorists like Professor Mani will go to work and tell us what this really means. And they predict in advance as well. That's best of all if they predict something and then we see it like Higgs did. So that's how it goes. Right. If particles interact with the Higgs fields to get mass, what is the role of the Higgs boson? So the Higgs boson is just, I'll try not to be too technical about this. It's to allow the Higgs field to provide the masses, this thing gets left over in the theory, essentially. The other new parts of the standard model you've introduced with the Higgs field end up giving you the masses of the W and Z particles. But there's one bit left over, which turns out to be the Higgs boson. So if you're using this Higgs field to describe the masses of particles, which we do in the standard model, you've got to accept that you're going to have this Higgs boson as well. And if it's not the right way to describe masses, the Higgs boson wouldn't be there. And many of these beyond the standard model theories I mentioned before, they have more Higgses. You would have multiplets of Higgses, and this is one of the active areas of research at the LHC, is to look for additional Higgs particles. So this would again tell us that there are more Higgs-like fields and tell us something about these beyond the standard model theories. Until now, quarks are the most subatomic particle discovered, right? Yes and no. So all those particles that I showed you in that image of the standard model, the quarks, the leptons, and the boson force carriers, they are considered elementary particles. They have no substructure. So the electron is just like a quark in this respect. Okay, they're all elementary particles. So why has the concept of dark matter been introduced? What would its discovery mean? So the concept of dark matter was introduced by a astronomer, astrophysicist, cosmologist called Fritz Zwicky to try and describe the observation that galaxies rotated much faster than you'd expect given the brightness of them, how many stars are in them. And only if you hypothesized that there was some matter you couldn't see, stuff not in the stars, which actually heavily outweighs the stars, could you describe the motion of the galaxies. So that led to its hypothesis, and further astrophysical observations, things like gravitational lensing, the distribution of the cosmic microwave background on the night sky. They all require dark matter to explain how we've observed them. Okay. Now, what would it mean if we directly discovered some evidence for dark matter which is not based around a large-scale astrophysical observation? It would tell us something about beyond the standard model physics if it's a particle solution. It would mean it's a new particle. It would give us some indication of which of these theories might be correct. For example, supersymmetry predicts there should be a particle that's a very good dark matter candidate, and it should be observed at the LHC essentially. Or there are other experiments dedicated to detection of dark matter that might see it. So it would point us in the direction of what theory beyond the standard model would look like. That's what it would imply. There are theories, there are explanations for dark matter that are not particle-based. There's one which is controversial, which modifies Newtonian dynamics. And others now, given what we're seeing in gravitational waves, it's possible tiny black holes have something to do with it, what are called primordial black holes. There's a small region that still allows that as a solution. So it may not be particle-based at all, but it will tell us something about the universe for sure. Which one? Which would give more understanding about matter, particle physics or quantum theory? So the standard model of particle physics is a relativistic quantum field theory that's locally gauge invariant. So I don't really disassociate the two things. Our description of particle physics is a relativistic quantum field theory. That's how we describe what we see. Okay, so they're synonyms. So will we be, sorry, I didn't need to say this, sir. Will we be able quantify mass? Can we find the reason behind why quarks are heavy? Maybe. Some theories reduce the number of parameters and give you a hierarchy of masses. So this is a very high energy behavior, then you evolve it down to a standard model, it gets broken along the way, and you can then describe these generations of masses. It really depends what this new physics looks like. You know, you could just give up and say that, yeah, nature is this. Nature just decided 3, and that's that. And there are a group of people who are starting to think that way. But it would seem more natural that we'll find a solution as to why 3 generations. Doesn't seem to be 4, doesn't seem, and definitely isn't 2. So why 3 in particular? But I can't give you any guarantees on that. At the very beginning of the universe, it is said that it contains slightly more amount of matter than the amount of antimatter. 1 to be specific. What made this slight imbalance? I don't know who said this. That's not necessarily true. Our understanding of matter and antimatter is given by a Russian physicist, Sakharov, who in the 1960s wrote down 3 conditions that are required to have a matter-dominated universe over an antimatter-dominated universe. And those three conditions are a means of baryon number violation, which kind of is what you're talking about. You would have had more baryonic-like matter than antibaryonic-like matter at the beginning. But our theory isn't like that. Our theory has almost equal amounts. So you have to have this antimatter asymmetry, what's called CP violation. And at some point, things must have been out of equilibrium. You couldn't have reversed the transition to go back to what you had before. So you had to have, so you've got to have non-equilibrium, you've got to have a difference in how baryons and antibaryons behave, and you've got to have a difference between how matter and antimatter behaves. That's all that's required. It doesn't mean that we had an imbalance at the beginning. It actually seems highly unlikely. It seems at some point as we went through the early evolution of the universe, the imbalance happened. Current theories most likely predict this was actually done using neutrinos. It's in the neutrino sector. That's the current favorite for how it would have been done. Superconducting wires are wires which I learned that develop such wires is not possible. Then how did then using, well, wherever you learnt this is wrong. Superconducting, you can make any metal superconducting almost if you get it cold enough. You can get a copper wire. And as it's cold enough, it will become superconducting. So once the electrons in a metal are cold enough, they interact in a special way to form pairs which essentially have no resistance as they move through the material. So I'm afraid you have to go away and learn a bit more about superconductivity. So look up BCS theory if you want to know how that works. No, can all particles in the standard model be present in a single molecule? The answer to that is no. So the neutrinos, probably the simplest answer to this, only interact weakly. They're too weak to form any kind of bound state. The interaction is just too weak. We only see bound states due to the strong interaction, the nucleons, mesons, hadrons, and we see electromagnetic binding of electrons into atoms. The other particles are unstable as well, so they decay away. But neutrino matter, I've never heard anyone, maybe you could think of some condensate of it, but I'm not familiar with it. But it wouldn't be in the one individual particle or molecule, at least. How was it determined that what was discovered as the Higgs boson was not what they expected? It was another new similar particle? That's a very good question. So there are that we don't really know the answer to fully yet, but the additional measurements that we've done of the Higgs particle all tie up with what we expect in the standard model. In a slightly different version of this talk, I show a plot where you have all the measurements of the Higgs coupling to different particles sitting on a line, which is what's predicted by the standard model. It's a very boring plot. We'd really hope that the Higgs wasn't the one in the standard model and that particles didn't couple in that way. That would tell us a lot more than it does. So in fact, the Higgs discovery has been a little boring in that respect. It hasn't shown us yet any window to physics beyond the standard model. It looks exactly like what we'd expect. But with this problem that we have to tune parameters in the standard model to 18 decimal places, which seems extremely unnatural. At high energy level, Higgs boson can have catastrophic effects. So how can it be controlled using modern physics? Okay, so there is an element of truth in what you're saying, but it's not something we would control. Okay, the Higgs potential in principle can make the vacuum unstable, and this is one of those problems related to this fine-tuning of parameters. The Higgs we see is no danger whatsoever when we produce it, but the theory as a whole could have given this Higgs field leads to an overall instability of the vacuum, and it would be a problem if that were violated. But it's nothing we do to control it, it's nature. Okay, if nature is that way, it's just we haven't seen it yet. So the lifetime for such tunneling to happen hasn't occurred yet in our universe. If it did, we'd know about it. How long will it take us to, or will we ever understand 100% of the universe? So the answer to the first part is, I don't know. All I can say is, if you'd told somebody at the end of the 19th century, there are all these famous quotes about how physics was finished, and it was just sort of engineering from now on, we understood everything. And then you have the massive revolutions that have taken place in our understanding of physics in the space of 120 years. So it's impossible to say what we might know more about the origin of nature in 100 years or so. But our progress, particularly in the last few hundred years, has been very rapid. So maybe it will continue in that way, or maybe we'll be stuck for a while. Who knows? Will we ever? Again, I don't know. It would seem unlikely that we'd understand everything. It makes science just to become a textbook subject would be rather boring, I think. I think research will probably always continue, even if it be just a very complex system. It maybe we understand particle physics, we won't be able to understand complex systems, which are very difficult to understand in emergent phenomena. No. So, sorry, could string theory refute all of the efforts till now? Absolutely not. So string theory has to accommodate everything that we've seen till date. That's a prerequisite for any new theory, is it has to describe the standard model at the energies that we look up to a few tera-electron volts. So all it will do is give us this quantum description of gravity as well. So but it's got to have the standard model there, and so our particles become these excitations of strings or branes or whatever particular flavor of string theory you prefer. Universe constitutes 95% of dark matter and dark energy, but are we unable to observe it? Yes, we do not observe it directly. We only infer its presence from astrophysical observation. So it's not observed directly. Is there a way to detect it so that we can harness it? No, at the moment, but perhaps your question marks suggest that we might be able to in the future, who knows? No, one assumption is empty space consists of dark energy, and this is the reason why universe is expanding. That is what dark energy is. It's a continual acceleration of the universe. It's pushing every point of space apart in the universe. Okay, and we're in an era now where the energy density of the universe has decreased to such a degree that it's starting to dominate. So this is what we mean by the accelerating universe. Dark energy is slowly pushing it apart. So it stops the idea of there ever being a big crunch. You know, the universe will just continue to grow, driven by this dark energy. It's a valid assumption to explain the data that we see. Okay, that's all I can say. It's another lecture to learn about physical cosmology. Could dark matter be made of axions? Yes. Very much so. So axions are a particle that was hypothesized initially as a solution to a very odd problem in the standard model, whereby we don't see any difference between matter and antimatter when they interact via the strong or the nuclear force. It's called the strong CP problem. And a way to fix that is to have an axion particle. This is what's called Pegiquin Theory. And they would be, that they don't interact very much. They're light enough that they behave in a way that very much fits the cosmological observations. And people are actively looking, including experiments I work on and at the LHC, for axions or axion-like particles as dark matter candidates. So that's it, I think, is it, Mr. Ireland?
Yes, sir. That was the last question.
Okay.
Thank you very much, Professor Libby. And you brought out a very important point that there's a lot of exciting work to be done. And
Absolutely.
So I think the younger generation should understand that this is going to be an exciting field for many decades, and many interesting experiments are down the line, especially on dark matter. Nowadays, many experiments are being done all over the globe, and all the best. Thank you very much again for the nice talk.
You're welcome. Thank you for the invitation.